Education pays off.
Hi, good evening. I'm very glad to be here with you with Robotic Solutions, and it will be a great pleasure to answer all your questions. I have prepared about a 20-minute video that explains the the work I did on the high-speed wireless communications and my vision for 5G and 6G. Hope you'll find it useful, and would be glad to answer any of your questions. Good evening. I hope you're doing well in these tough circumstances of the pandemic around the world. Hope you're in good health and taking good care of yourselves. It gives me a great pleasure to be talking to you through this video, and I will be with you live to answer any questions you may have. My name is Hatim Zaghloul, and together with a fellow Egyptian, we developed two technologies related to wireless communications, and very fortunate for us with timing and everything else. These two technologies are the foundation of all modern high-speed wireless communications. Basically, these two technologies are the WOFDM, the wideband frequency division multiplexing technology, and the multi-code direct sequence technology. Basically, the story is simple. I come from a middle-class family in Egypt, and I studied a lot. I don't want to talk about how much I studied, but I read a lot of books that were extracurricular and did a lot of activities. I was responsible for the library when I was in preparatory school and things like that. So I really studied a lot. My studies were in electrical engineering, in communications, and I did a master's. I did a BSc in mathematics and a master's and a PhD in physics from Calgary, Canada. In any case, just at the time I was finishing my PhD around 1989, I was recruited by the phone company in Alberta in Canada called at the time Alberta Government Telephones, later became TELUS, which is now a big phone company in Canada. In any case, TELUS asked me to lead a project to define their offering of 2G, the second generation of mobile telephony. The first generation didn't come to the third world, and it was just basically an FM radio. Anybody with an FM receiver at the right frequency could just tap in and listen to a phone call if he was bored. So I started looking at this. Got very lucky. I first asked them if I could solicit the help of my friend Michel Fatouche, because Michel had done a PhD in coding and modulation. I had moved away a bit from communications, so they agreed and Michel agreed. So we together started working on this project. And the bigger luck was the phone company TELUS bought the biggest phone manufacturer, mobile phone manufacturer at the time, which was a Canadian company called Novatel. And Novatel said, well, since you are leading this project to define the best 2G technology, lead it for us too. So that was a big step to define 2G for the biggest phone manufacturer. And suddenly, from just working with a friend of mine, I had 24 team members. Some of them were PhDs in communications. So suddenly it became a very serious project, and it took 6 months. And we concluded that was in early 1990, March 1990, that the best technology offering was GSM, the one that got utilized in most of the world. And GSM was not available at the time. So we told them that if they wanted to do something immediately and they had plans to launch quickly, we said use something called IS-54, Interim Standard 54 from the TIA in the US. And that was a standard that was already available. It was a step between FM and the full GSM. It was smaller bands than the GSM. In any case, at the end of the report, we wrote that all these technologies are bad. And so I was asked, why are you saying it's bad? So we wrote in the report, because the maximum speed of GSM, which was the best of them, was 256 kilobits per second. And we said, once you give people a taste of wireless internet, they're not going to be satiated with anything short of 10 megabits. So we wanted the first technology to come out, digital mobile technology, to be 10 megabits. They said that's impossible. You can't do 10 megabits on mobile and things like that. So Michel took it to heart, and he recommended to me after 6 months that we use technology called OFDM. OFDM is simply the concept of giving a single user more than one frequency, and they could be adjacent or not adjacent, but to give him more than one frequency at the same time. So imagine when you use FM radio, the FM band itself is only 50 kilohertz, but the actual band allocated is 200 kilohertz. The reason they waste this extra 150 kilohertz is because the radio may not be accurate and it may shift. You don't want to pick the wrong channel. So, but if you give someone 2 or 3 of these channels, you save these 150 kilohertz, at least for 2 of them. Say if you give him 3, for 2 of them you will save it and you get a higher bandwidth. With digital techniques and the fast Fourier transform and so on, we can actually make the spectrum practically perfect. So it looks practically like a box. And this way, we have the efficiency of utilizing the bandwidth much higher. On the average, we can get a 10 times better efficiency than in, just regular FM. Of course, we don't use FM, but we use, digital modulation techniques. So Michel brought me this technology and, showed it to me. It was known before us. It was invented in, I believe, 1956 or 1957. I looked at it and said, but it still has a few problems. There was no channel estimation in it to fix for the channel problems. There is another big problem in what's called packet communications. If you recall, before all this, there was something called carrier recovery in radios. The carrier recovery had the function of ensuring that the receiving station had the same band or as the same frequency as the transmitting station. So there was a circuitry inside the receiver to lock the transmitter, the receiving frequency to the transmitting frequency. This process took 5 milliseconds. You can imagine now if you have a packet transmitted and the packet is, say, transmitted at 1 gigabit per second, that packet, if it's 1,000 bytes, is going to take, less than 1 microsecond to be transmitted. If you take 5 milliseconds just to synchronize the two radios, that's a huge waste. As we say, the payload is very short compared to the synchronization. So what we came up with is digital carrier recovery. So you bring the two frequencies, by virtue of crystals and so on, close to each other, and you do the rest digitally. So we did digital carrier recovery, digital timing recovery, and we introduced channel estimation. We put some techniques to make sure you can do wideband OFDM. There were recipes in books that told people don't do wideband frequency division multiplexing, because what you end up with is, if you're transmitting in a big band, some of the frequencies in the beginning of the band can see a different channel than the frequencies at the end of the band. And how do you equalize for that? Well, we introduced channel estimation. You just transmit a frame or two at the beginning to know the channel and use that information to fix the rest of the signal. In any case, wideband OFDM had the simple beauty of reducing the amount of processing that's needed to do high-speed data communications, and they reduced the amount of processing needed to equalize the signal. So basically it became, you give me frequencies, you give me a bandwidth, I give you data communication speed. So, all future, since 1995 or 1997, all high-speed data techniques use OFDM of sorts. The second patent we came up with was this multi-code direct sequence spread spectrum patent. And basically it was a concept that we introduced in the OFDM, which is as you take, the data is made into symbols. A symbol is a number of bits. So in, say, Wi-Fi, you have 64 symbols beside each other. If all these symbols are one, and I'm simplifying things. If all these symbols are one and you add them together, you possibly get 64. And if they're all zeros, you get 0. So suddenly a signal that was 0 and 1 became 0 and 64. The dynamic range of the amplifier is reduced appreciably. So, that's not good. You need linear amplifiers, which are very costly on power and, expensive. So we came up with the idea of take each of those symbols and before you put it in the Fourier transform, randomize it with a complex phase. So we introduced random complex or complex randomization. But in the case of OFDM, it was only with a phase, not an amplitude. Just change the phase so that you don't align all the ones. And, we applied that to also CDMA, which is a concept of codes, not frequencies, and got the same result, which is, they reduced the peak to average problem and made it practical. So that is what they used in 3G and used in 4G and so on. So LTE in the uplink uses this, LTE uses in the downlink the OFDM as it is. Now the world learned of our technology and standardized on it in the Wi-Fi in the year 1998. It was standardized in 5 gigahertz because the US didn't allow OFDM in 2.4 gigahertz. So we actually applied to the FCC because we had a device. And in February 2000, we applied, and of course they quickly rejected. I gave them about a 30-page explanation why they shouldn't have rejected it, that it complies with all the spread spectrum laws and rules of the FCC, from the processing gain to spreading the signal and all that. So we showed them all that by measurements, so we complied with the law. They wrote us a letter back saying, no, it's still rejected. You comply with the rules, but you don't comply with the spirit of the rules. So of course we took that to a lawyer. What's the spirit of the rules in engineering? And we appealed then to the commissioners of the FCC in the United States. And in May 2001, we were vindicated. They said the FCC was right in rejecting our application, but our application is very good for humanity and for the efficiency of using the bands. So they allowed our product to be sold, and anyone that complied with the rules that we had set for ourselves gets certified to be sold until they change the law. And they changed the law now. The 2.4 gigahertz is the most widely used band for these high-speed data communications devices. So I'll leave the product now. In 2002, we started the WiMAX forum. We meaning my company, WiLAN, and my former company, WiLAN, and I had also something called the OFDM forum. Together with Nokia and an Ensemble, and WiLAN later acquired Ensemble and another company. These 5 companies started the OFDM forum, and by virtue of owning Ensemble and the OFDM forum, or we were the head of the OFDM forum, we basically had veto power in the WiMAX forum. And we developed a WiMAX technology that was beautiful to use outdoors. It was not set to go through a cement wall and still work well. So what our plan was, make a technology for outside that is very similar to Wi-Fi, so we can use the same chips for both. And we did that with a near line of sight WiMAX 2004 standard. Anyway, the 216E. And it was a mobile standard, but it had limited mobility. We proposed that standard in as I said, 2004, and it got approved and it got adopted. And in 2005, my company was going through financial troubles. So they asked us to leave the control of the WiMAX forum, and we did. And unfortunately, they rushed. And they made WiMAX a full mobile technology, saying it works indoors and outdoors. They had tested in a country like Israel, where the buildings are only 2 stories high, in the town that it was tested in. Well, of course, when they applied it to New York and the big cities, it didn't work. So unfortunately for the WiMAX, it became now only a technology for backhaul and the infrastructure building of networks. And of course, we used to badmouth the cellular industry's technique to get to 4G, which was, we called it the long-term evolution. Either you get into 4G with a revolution using WiMAX, or with the long-term evolution of the cellular industry. And of course, they shortened it to LTE, and it became the most famous 4G technology. So in any case, we did that, and so we had a big our fingerprint is all over, the Wi-Fi, 3G, 4G, and now the 5G. I want to talk now about the future a little bit more. Of course, we had envisioned, when we developed our first patent in 1992, that the purpose of this patent is to facilitate communications between anybody and anything, anywhere, at any time. So it was really ubiquitous personal communications that involved IoT. But you cannot have Internet of Things without having Internet. So Internet has to be pervasive, has to be everywhere in the world before we can do IoT properly. And so there is 2 schools on this. The school, of course, that is going now with 5G, and are proposing a form of 6G that are very fast, they're talking about, say 30 gigabits for 5G, and maybe, 1 terabit for 6G. I don't agree with these speeds. I don't believe, I agree that we should develop them, but I don't think we should have them in the mobile network. There is no mobile device in existence today that can handle these speeds to use them. If a processor is only 2.8 gigabits per second, by the time it takes a bit, gives it from the RF to the memory, it's probably 4 cycles already. And, so it's 700 megabits is the maximum it can beneficially use. So there is no point in having a mobile system that is in the 30 gigabits and a 1 terabit level. We need them for other things. We need them for IoT maybe. We need them for machines, but we don't need them for mobile users, with all the health risks they could bring. Because in the rush to get these things passed, we don't check the health consequences of them. The band that's proposed for the 6G, I believe, for the 5G, that is the higher frequency ones, the higher speed ones, is around 60 gigahertz, a little below 60 gigahertz. 60 gigahertz is the peak absorption of oxygen. So you can easily get bad effects. I'm not sure what, and I'm not scaremongering, but I'm just saying we don't need health risks with our new technologies. By all means, we should measure and do a lot of checks before we use the technologies. 2.4 gigahertz, below 10 gigahertz has been studied appreciably because of radars and things like that. So we have proposed a 6G technology that's based on, number one, blockchain. Let's say that the telecommunications network is still the same concept since shortly after Alexander Graham Bell in the early 1900s. And what I mean is, when you make a phone call, whether it's mobile or landline, you go first to a central office, it looks at the number you're calling and connects you to another central office and to the other user. This is an archaic concept. With the advent of blockchain, we can easily decentralize the centrals. So if we can have a mesh Wi-Fi network that covers, a university campus or a compound where people live or a small village, this could be phenomenally inexpensive, and at the end of the Wi-Fi, you put a blockchain computer server that knows the users in its area and labels the users with its ID. If they move to another Wi-Fi network, they immediately get recognized. They are from another blockchain server, and the blockchain server goes and gets their information from the other one, and there gets, with the blockchain nature, there gets to be updates of the billing and authentication and authorization at all times. So this way we can reduce the cost of new networks by a factor of 10 to 100, because currently, if you want to build a telecommunications network, you've got to put a central office, an IMS, and all kinds of switches and things like that, and DSLAM and all these things. You don't need any of this anymore. There's a decent infrastructure, and if there isn't, you use microwaves to move the signal, and you get people on the internet. 3.5 billion people are not on the internet because of the cost of the infrastructure. So we need to move away from just speed, which was a race, unfortunately, that we started in 1992. But now we need to slow down and think of inclusion. We want to include all the world in these developments, and we want to think of the rest of the world to bring them on the internet and let them have the benefits of the internet. I hope this was useful. If you have any questions, I would be glad to answer them, and we will have a live session to answer live questions, and I hope the organizers will also have this online, and you can ask questions, and I'd be glad to answer them anytime in the future. I wish you all the best, and I wish that you stay in good health with this pandemic, and you continue learning. Learning is the top priority in the world at all times. Thank you very much, and all the best.